record on this computer. I will share my screen, my computer sound. Okay, well, today I wanted to continue our discussion on additive synthesis and synthesis in general. We had been talking about different forms of synthesis, how basically it's, the idea about synthesis is just, it's kind of a varying sort of concept. You have agency in the process, in other words. Like you basically are having some sort of hand in the design of the sound. And there's so many different ways you can do that. You could sample a sound as we've done with Simpler. But you could also use this technique called additive synthesis, which is a really interesting form of synthesis. In order to understand additive synthesis, I realized that we might have to pull up a little bit of trigonometry. I know you might have thought that you never had to look at that again, but it's funny, of all the subjects that are ridiculed in school, like trigonometry, it's got a bad rep when you're studying it. It's actually one of the neatest subjects you could possibly explore, from the standpoint that waves are just abundant. They're all around us. They're very important from a musical perspective. So I kind of wish, from my own standpoint, I was paying attention more in trigonometry class in high school. And but it's quite fascinating. So I won't go too in depth with it. So don't worry about if you have an aversion to mathematics. Don't worry. We won't cross your threshold of pain. I don't think. We'll just gently introduce some of the concepts. Just to kind of go back a little bit, there's this idea that you can pattern, you can generate certain types of waveforms by using an oscillator. So if you imagine a car engine, right, it spins kind of regularly in a very cyclical manner. And as a result, as you actually press down on the gas, you increase the RPM, the revolutions per minute, which is related to the cycles per second, or which is a measurement of frequency. So as a result, as you push down on the gas, you actually hear the car engine increase in frequency, right? You hear it go, right? You hear the pitch get higher. You also can imagine a table saw, right? I like woodworking, so I use certain tools in the garage, like saws. But you might like cooking, and you might turn on your blender, and you might hear the blender. As you turn on the blender, you actually hear that spinning component of your blender actually increasing in pitch, right? If you turn on your Vitamix, as you increase the blending speed, you actually hear the frequency getting higher. So in many ways, these are all oscillators, but on a synthesizer, it's not necessarily practical to put a Vitamix into your synthesizer. So instead, we use these things. There are many different designs for oscillators in the analog world, meaning a physical device that produces sound is kind of an analog device, whereas in the digital domain, we're actually not physically creating these particular we're not actually creating these airflow disruptions using like physical mediums like a car engine or a blender. We're actually getting the computer to generate these waveforms, which ultimately get converted to sound, which we hear in the real world. But there's, I guess you could think about analog as being kind of a continuous process, whereas digital is kind of a discrete process that occurs on the machine. So ultimately, when we're in the digital domain, we're kind of simulating what an oscillator in the real world does, like a car engine spinning or a blender rotating, right? But for all practical purposes, you can kind of visualize them in the same way. That's like not a point we need to think about too much for now. The point is, the algorithms that we use are called oscillators because they're simulating these physically rotating devices in the world which can produce sound. Remember, the reason that we hear frequency is because we hear a certain patterned repetition of air pressure variations. We register these patterns as frequencies. So the more patterns we hear per second, the higher the frequency. The less patterns we hear per second, the lower the frequency, right? So anyway, so oscillators, you know, depending on the mode of the thing that's spinning, you can get many different waveforms that result. So, so for instance, a sine wave is a very special kind of wave. So if something is spinning in a perfectly regular manner in certain conditions, you will get a sine wave. Whereas let's say that you're not rotating around a circle, but there's some sort of friction, or there's some sort of, like, your car engine might have some spokes in it. There might be some like divots in the engine itself as it's spinning. It actually isn't, it's not like a regular surface, so it's not producing a perfect sine wave. It might produce another waveform. It doesn't sound like a sine wave. I haven't played you what a sine wave is, but I can play you a sine wave. Oh, thank you so much. All right. Sorry, excuse me for one moment. All right. So let me actually pull up a sine wave. You know what? I can do it a different way. This is a sine wave. Let me actually turn on my audio in pure data. This is a sine wave, or this. Can you hear that? Okay. It's a very kind of pure tone, right? So you can kind of imagine, let me turn this off. You can kind of imagine that there are a variety of different waves that can be generated, right? It's not hard to believe that there are a lot of different waveforms that can be generated. All of these particular waveforms have the same frequency, meaning, like, if you count the number of repetitions that occur, there are 3 repetitions of this shape, right? Whereas there are 3 repetitions of this square shape, whereas there's 3 repetitions of this triangle shape, and there's 3 repetitions of this sawtooth wave shape. So the idea is, depending on the physical characteristics of the oscillator, the actual mechanism that's spinning, you can generate all of these different waveforms. So in the digital domain, it's very easy for an algorithm to generate all of these different waveforms. And what's cool about them is that you actually get a lot of sonic versatility. Whereas all of these are the same frequency, square waves sound quite differently than sine waves, and triangle waves, they all sound different. They all have their own unique characteristic. So when you're actually synthesizing a sound by aggregating all of these different sounds together, you get some interesting sonic results. And we'll talk more about that. So just kind of going along the idea of adding sounds, there's a lot of interesting stuff that you can do with adding sounds. So just to kind of recap, I made, there's an app on the Mac app called Grapher. So I made a couple of graphing apps, or graphs, I guess I should say. So I just want to show you this idea of wave interference, right? So if this is a sine wave, right? If I take the same exact sine wave and I shift it so that its phase is, basically I'm taking the sine wave and I'm shifting it over, right? It's the same exact sine wave, but I'm moving it over to the right or to the left. In other words, like, this is an example of shifting it. This is the same exact shape, but I'm just moving it right on the graph. I'm changing the phase of the wave. Now, if I add these 2 waves together, basically what this means is I'm basically taking the point of the wave. I'm taking 1 point of this equation. So let's say I'm taking this point of this equation, and I'm adding it to this point on this equation. And if I do that, it actually cancels out, right? This plus this just cancels out right here, right? Whereas if I do this, if I add this point to this point, it also cancels out, right? So in other words, if I take these two waves and I add them together, you actually get nothing. They completely cancel each other out, right? Because when you add waves together, they you just point by point add up the contributions of each wave, and then you get the resultant wave. In this case, the waves perfectly cancel each other out. So if I show you another example of this, let's say the waves can actually reinforce each other. So in this particular case, you have this wave, and then you have the same exact wave, right? This is one wave. This is another wave. They're the same exact wave, and you can see them both. They actually perfectly overlap, so you can't necessarily tell which one is which. But if you add these two waves together, they perfectly reinforce each other. So if this value was 1 for the first wave, and it's 1 for the second wave, if you combine the waves, you get 2, right? If it's 0 for the first wave and 0 for the second wave, and you add the contributions of both waves, you get 0, right? It's just addition, right? You're just adding the contributions of each wave, and you're just looking at it on a graph, right? So similarly, you can add together a bunch of different waves in this manner. So we're going to talk about the harmonic series, which is a very interesting case. And the idea, I guess, I want to tell you is that, yes, you can add together these waves and you can result in richer waveforms. But there's something very interesting that is worth talking about, which is the harmonic series. It's this idea that actually this square wave, this triangle wave, and this sawtooth wave can all be generated by sine waves and the harmonic series. So this is a really cool topic. I love talking about the harmonic series. The idea behind the harmonic series is that there are a bunch of waves that are mathematically related to each other. And you can add these waves up, just like we did previously, to result in new waves. So very simply, the harmonic series is you basically take a frequency, and then you take 2 times that frequency, and then you take 3 times that frequency, and 4 times that frequency, and 5 times that frequency, and 6 times that frequency. So basically, you have a sine wave at all of these frequencies, right? So if this is sine of x, this is sine of 2x, right? So if we're looking at the sine wave equation, if you remember good old sine of ax, right? A is the sine of fx, right? F is the frequency, right? So if we do sine of 1x, essentially, if we're looking at this particular graph that I've made, sine of x is just basically, you see one particular cycle of the wave, right? Whereas sine of 2x, you see 2 repetitions of the wave, right? Sine of 3x, you see 3 repetitions of the wave, right? 4x, 5x, all the way to P90x. But basically, you see these increasing repetitions. And it's very easy to convert this to that, right? Because it's just 1 times the frequency, 2 times the frequency, 3 times the frequency, right? That's what it looks like on the graph, right? So the idea is, if I actually took all of these particular waves and I added them together, I would get this. Now, actually, let me change my, gosh. Right, in fact, I can just do this. Right? No, I can't. Give me a second. Okay. If I added all these waves together, I would actually get a wave that looks kind of interesting, like a different wave, right? If I added sine of x and sine of 2 of x and sine of 3 of x, I added all these waves, I would get this other wave, right? And all my equation is this, sine of x plus sine of 2x plus sine of 3x, plus sine of 4x, etc., right? Now, what's interesting is if I weight these waves in a certain way, so let's say I take this wave, if I take these particular amplitudes, so let me just go back to the sine wave equation really quickly. If you have this equation, if you see this equation, A in front of the term is the amplitude of the sine wave, right? How loud the sine wave is, the amount of fluctuation in the air pressure, loudness, right? The density of the air pressure. The frequency is the number of repetitions, right? So if I just play around with these two terms, so like the amplitude, if I go 1/3, if I look at this, so I go sine of x plus 1/3 sine of 3x plus 1/5 sine of 5x plus 1/7 sine of 7x. And what I get is actually a square wave. It was one of those waves I was talking about over here. It's one of these waves over here. So what I wanted to show you was this idea that you can actually generate other waveforms just by using a simpler waveform and just kind of creating, adding together multiples of that particular waveform. And you can generate all kinds of interesting sounds that way. So in other words, a square wave can be created from a sine wave. A triangle wave can be created from a sine wave. A sawtooth wave can be created from a sine wave, okay? And so, with that being said, I can show you an example of this, right? An example of generating all these different timbres. So let's say I have this particular low frequency. Oh, wait a second. Volume a little bit. You can see that as I add harmonics, what I'm basically doing, let me just explain what I'm doing here. What this particular thing is showing you is all of the different harmonics of a sound. And all of these harmonics are just multiples of this frequency right here. So if this frequency, let's just use a simple number. If this is 40, this is 80. The second harmonic is 80 hertz. The third harmonic is 120 hertz. The fourth harmonic is 160 hertz. You see how this is just 40 times 1, times 2, times 3, times 4, times 5, right? And as I change around the volumes of these relative harmonics, right, you can see how the actual waveform changes. And the sound sounds different. So let's say I just played the odd numbered harmonics. Right? So this is 40 hertz. I'm going to add a little bit of 80 hertz. You can kind of see how there's two cycles, right? A little bit of 120, a little bit of 160. So basically, I'm adding together all of these particular harmonics together, and I'm kind of choosing different loudnesses for each of them. And the result is I can get all kinds of interesting sounds this way. And if I change the frequency, it kind of sounds like a chord also, which is kind of interesting. Right? But as I change the fundamental frequency, it actually sounds like a single note, a single pitch. So this is important because there's a lot of, I mean, this is just good to know for one, but it's also, there are certain synthesizers in Ableton that take advantage of this particular fact. So I'll show you one example of a synthesizer in Ableton that takes advantage of this. So if I go to the synthesizer called Operator, if I actually, I have to know exactly where to go. But if I go to the oscillator section, I guess really quickly, I'll just tell you, there's 4 different operators here. Basically, different places where you can adjust you can choose the oscillator and where you can choose the envelope of the particular oscillator. So if I choose the first oscillator, the first operator, and I go to the oscillator section, let me actually figure out which track I'm working with. Rename this operator. Okay. And what I'm going to do, I'm just playing this particular sound right now. Right? And what I get is a sine wave. Right? It sounds like a sine wave. But if I wanted to, I could actually choose the different waves from this particular graph, from this particular dropdown. So I could go to a saw wave. And what you're seeing is basically each of these little bars on this bar graph are representing the different harmonics in the sound. Okay? So in this particular case, for a perfect sine wave, what's interesting about a perfect sine wave is there's only one harmonic, which is the fundamental. Right? So looking back at our particular patch, if I just turn up the first harmonic, we get a sine wave, right? But if I add any other harmonics into the picture, we don't have a sine wave anymore. Like the combined result of these two harmonics won't result in a sine wave, right? So the idea is, if I have one harmonic and only one harmonic, what I'm going to get is a sine wave. Now, if I go to a sawtooth wave and I choose saw 16th, saw 16, what this is going to say is it's going to build a saw wave with 16 harmonics. Okay, so I'm not going to actually do this, but if I actually made the shapes of all of these blue faders match this little graph right here, I would get the same exact sound that you would hear that I'm playing right now. Right? So if I go to a square wave, for instance, what you're actually hearing, what you're seeing and hearing are only the odd numbered harmonics, right? So it's basically, it's going to have a volume at the first harmonic. There's going to be no volume on the second harmonic. There's going to be volume on the third harmonic, no volume on the fourth harmonic, volume on the fifth harmonic, no volume on the sixth harmonic, etc., right? If I choose 64, a square wave with 64 harmonics, basically, it's still only going to use the odd numbered harmonics. And you can see basically how the intensity of the harmonics decreases over time. So the first harmonic has the most intensity, whereas if you keep going, it kind of fizzles out, right? They kind of stop gaining intensity, right? There's less and less and less intensity, and it kind of plateaus, right? So the idea is, what's cool about this particular synthesizer operator is it allows you to construct different sounds by messing around. For one thing it does is it allows you to construct different sounds by messing around with the harmonics in the harmonic series. So a triangle wave, this is basically the equation for a triangle wave. And what's interesting about this is it's very similar to a square wave, but the math on how loud each of these harmonics are is slightly different than a square wave. So you can actually, in this particular synthesizer, you can actually draw in your own shapes. This is pretty much identical to what I made in this particular software. So you can see what it sounds like to mess around with the harmonic series. So remember, each of these bars represents different harmonics in the harmonic series. And each of the bars is basically representing a note that is an integer multiple of the previous, of the original frequency. So like looking back at our original graph, if the first bar was sine of x, the second bar is sine of 2x. That's the frequency is 2 times the original frequency in the first bar, right? The third bar has a frequency that is 3 times greater than the frequency in the first bar. Whereas the fourth bar, right here, 1, 2, 3, 4, has a frequency that's 4 times greater than the frequency in the first bar. So you can construct all kinds of interesting sounds this way, but this is all basically, and this is all related to additive synthesis, right? Because you're basically adding together all of these different sine waves to create a timbre, a particular sound, right? Which is sort of interesting. It's pretty mind-blowing how versatile a simple sine wave is, and how a simple sine wave can actually generate all of these different sounds. So for instance, I've kind of showed, I've included explanations, right? So this is a sine wave, and you can kind of see the blue sliders control the volume of the harmonics, whereas in this example, the first slider has volume, whereas all of the other sliders have no volume, and you get a perfect sine wave. But if you kind of create certain shapes with these sliders, you get different sounds. So here I get a triangle wave, right? I'm approximately getting closer and closer to a triangle wave just by trial and error. So what's amazing is almost any sound in the world can be represented by using, well, every sound can be approximately represented by using the harmonic series in some way. So for instance, if you want to create a piano sound, you could kind of utilize these particular shapes, and it's a little more complicated than that, but approximately correct what I'm telling you, is you could use these shapes and apply them to operator, and you will get something that sounds somewhat like a piano sound. And similarly, if you want to create a violin sound, you could take these shapes and you can get something like a violin sound. It's not completely correct, but it's approximately correct. The reason it's not completely correct is that sounds in the real world are not totally harmonic. So what I mean by that is, if we take a sound, basically every single thing that this algorithm is generating is completely harmonic. Meaning every single frequency that's in this picture is going to be a multiple of this first frequency. This is a perfectly harmonic sound, right? But sounds in the real world are not perfectly harmonic. So to give you an idea, when you're looking at an EQ, right? When you're looking at one of these little equalizers and you're looking at the sounds, right? Let's say we took an EQ and we looked at a clarinet sound. What you would see is you would see a peak on the first harmonic and the third harmonic and the fifth harmonic, right? And this is due to the fact that a clarinet, the physics of a clarinet, you see harmonics at these particular odd numbered values, right? So if this frequency was 100, you would see a harmonic at the frequency of 300, and you would see a harmonic at the frequency of 500. However, you're also seeing a bunch of other stuff at random places. You're seeing like other sound at other places. And that's because the physics of the clarinet, or the physics of mostly any real world instrument, doesn't lead to perfectly harmonic sounds. However, using a computer, you can approximate the sound of a clarinet by kind of putting this kind of shape into operator. And that's why, that's one of the reasons why it doesn't sound exactly like a clarinet when you're like, oh, I followed this formula, and why doesn't my algorithmic piano sound exactly like a real piano sound? One reason is because in reality, the piano isn't perfectly harmonic in nature. And a violin sound isn't either, and a clarinet sound isn't either. But with that being said, you can kind of apply the shapes of the harmonics and transfer them into synthesizers, and you can kind of get something that's sort of similar in timbre to the original sound. which is pretty neat, I think. It's all related to additive synthesis and the harmonic series. In your own practice, you may or may not actually design sound at this granular level. You might not want to do this, but I think it's useful to know that this exists. It's very interesting also because all of this representation that we're seeing is very, very similar to what we've been seeing when we look at an equalizer. So for instance, if I open up an equalizer, right, you might think that, doesn't this kind of in some way look somewhat similar to this sound, right? Like, doesn't this representation look somewhat similar to this? You kind of see it sloping downwards, you kind of see it scooping upwards. Let me actually do this. You see it kind of sloping downwards, you see it sloping upwards, and you see it sloping downwards, and you see it sloping upwards, right? So what we're looking at when we're looking at an equalizer is actually kind of an analytic representation of what we can generate using additive synthesis, right? So let me actually go one step further and let me add in an oscilloscope. And an oscilloscope is kind of a way to see the sound in, it's basically a way to...
Can I ask a question?
Sure.
Either in operator or in your pure data patch that you've created, is there a way to import specific real world acoustic waveforms and see the components to, you know, to go the other way rather than like creating the partials, but to actually import the waveform and then see what the partials are?
Unfortunately, my patch and this patch doesn't have that capability, although it wouldn't, I'm sure there are synthesizers that exist that do have that capability that are downloadable, but that's a cool process, right? Like importing a particular shape, like for example, importing this particular shape into this, into the operator synthesizer. It doesn't, there's no direct way of doing it except by manually doing it one by one, but there are other softwares that I'm sure can do that. So this is basically just to kind of explain to you these different different ways of metering, right? What you can see on an oscilloscope is basically it's air pressure over time. So you're basically looking at these particular, you're basically, you know, we're looking at the air pressure of the sound, and by looking at the air pressure of the sound, you can actually look at and kind of get a bird's eye view of the frequency of the sound, of the loudness of the sound. But it only goes so far. When you actually have like for these particular sounds, you can kind of look at these sounds and get an idea for the frequency, right? Because they're simple waveforms. You can kind of see what is repeating, right? You're like, oh, there's 3 of these particular sine shapes, or 3 of these particular square shapes, right? But what if I gave you something like this? What if I gave you a waveform that looks like this? Would you be able to tell how many repetitions are occurring? Like, even if you zoomed in, I don't think it wouldn't be easy to tell, because this waveform is so complicated that you wouldn't be able to tell how many repetitions are occurring over a given window of time. And therefore, it doesn't really give you a good insight into frequency. Like here, you can clearly see, oh, there's 3 repetitions, and you can tell that there's a frequency of 3 hertz right here, right? So an oscilloscope is useful to kind of get a sense for how the waveform looks like, the shape of the waveform. But if you actually want to know the frequencies within the waveform, an equalizer is really good at showing you, right? So for instance, let me actually go to a simple sine wave. And you could see there's a simple sine wave right here, and there's exactly 1 peak in our equalizer, right? You can see that there's 1 frequency right here, right? Let's make the waveform a little more complicated. Now I'm going to add 2 frequencies. you could kind of see that there's like two peaks, right? There's like a second peak here. So you can kind of tell that there's two frequencies, but it's getting harder to tell, right? But right here on the equalizer, FFT representation, you basically see two peaks. Let me add like many harmonics. How in the world could you tell how many frequencies are here? You can tell right here by looking at 1, 2, 3, 4, 5, 6, 7, but that's because you've made the sound and you know that there's 7 frequencies in the sound, right? But it's really hard to look at this waveform and say, ah, there's 7 different frequencies here, right? Whereas if you look at the actual spectrogram, you can see there's 1, 2, 4, 5, 6, 7. Amazing, right? So the different tools of analysis are useful in different ways, right? So this is an oscilloscope. Remember, it's just looking at the air pressure over time, so you get a shape of the waveform. So it's useful if you want to like look at a saw wave and you can be like, ah, this looks like a saw wave, right? Or this looks like a square wave, right? But you don't have an idea that there's actually 32 pitches here, right? But you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc., all the way to 32, right? So what I'm getting at is that this equalizer representation that you're looking at is actually kind of it's basically an analog to these particular this additive synthesis that you're generating right here directly relates to what you're actually looking at over here, right? Because in the real world, sounds are much more complicated than having one frequency. There's many frequencies in the sound. So an EQ can actually tell you what frequencies are in the sound, right? I know that's a lot of information, but it's interesting. All these concepts are related to each other, and I think it's important to understand these concepts because when we talk about compression and we talk about some other issues, it's just getting an understanding for the harmonic series, I think, is really valuable because you see it all the time. Every time you open your FFT, you're really getting a bird's eye. When you're looking at all these peaks that are arranged like this, these are all organized by the harmonic series. The frequency of the first peak is 1/2 the frequency of the second peak, and et cetera, and et cetera, and et cetera. 1/3 of the third peak, 1/4 of the fourth peak, right? Okay, so let's actually open up a synthesizer that I think is a good synthesizer to start with. We won't start with operator. Let's start with analog. Okay, so I'm going to open up. I'm going to go to audio. I'm going to go to instruments, and I'm going to go to analog, and I'm going to drag in just a default instrument, right? So you can kind of get a sense for where we could go by adding together a bunch of different waveforms, but let's just start a little simpler. So the idea behind analog is that, for one, you have 2 oscillators that you can play with. So remember, an oscillator is just a spinning contraption, and depending on the mode of how it's spinning, you get a different sound, right? So you can actually choose different sounds. You can choose like a sine wave to be as the oscillator, right? You could choose a square wave. You could choose a triangle wave or a ramp wave, and you could choose a noise wave, which is basically just, it's basically like a very unpredictable waveform that's changing all the time, that doesn't have any regular shape. So for instance, if I looked at all these particular waveforms using my oscilloscope, we'll just kind of clarify that they are indeed what they say they are. By the way, this plugin is free. It's a great plugin to kind of do some analysis. So I'm going to go to the sine wave. Ah, good old sine wave, right? Our good old friend, the sine wave. Now let's go to sawtooth. Okay, wonderful. Let's go to a square wave. Let's go to a noise wave, right? There's no organization to it. It's just totally random, and it's intentionally random, right? So let's, for this particular example, let's construct a sound. Let's start with a sine wave, okay? So oscillator 1 has a sine wave. Let's open up oscillator 2. Or actually, before we open up oscillator 2, let's just trace what's going on here. Because every synthesizer is different, okay? So what's happening here is that the sound is starting in this particular oscillator, right? And if I click this oscillator, I can actually look at particular controls, like the pitch envelope, right? So the pitch envelope, what would I want to use the pitch envelope for? Well, remember, it's like you're basically automating the parameter of a single note for a single note. So for instance, if I play a single note, I'm basically going to automate the pitch for that note. So if I raise this value, right? So I'm going to go back to the oscillator section, and basically this is the shape of the pitch over time. Okay? This may not be what you want to do, but if you want to get kind of an alien spaceship sound, you can mess around with that parameter. You can kind of get this cool kind of laser beam kind of sound, right? But for now, I'm just going to leave this pitch envelope alone. And remember, the graph usually has controls that verbalize what these parameters are. So the pitch envelope initial really is like, in some ways, it's like the, yeah, it's just the initial value of the pitch attack. It's like the, that's what it is. It's an envelope, but you don't have controls, the same control of the envelope that you do for the other envelopes we've been studying. But you can kind of see that it's basically a graph of the pitch over time. Higher pitch, going to lower pitch, right? Okay, so when you click this little oscillator, you see this envelope. You see some pitch envelope stuff, and then you see some other stuff. You see this pitch mod, and you see this pulse width, and you see this sub/sync. Let's just look at this pitch mod really quickly. So for pitch mod, what does this mean? We're basically trying to modulate the pitch. But aren't we already doing that here? We are modulating the pitch here, aren't we? Right? We're changing the pitch over time. That's modulation. But what does this mean? This means that we can, basically, it's a dry-wet control for the LFO. Okay? So the LFO, remember, the LFO is this idea that you can basically change the pitch in a periodic, you can change any value in kind of a periodic manner. So if I turn on the LFO, notice how it's not lit up right now. But if I turn on the LFO and I go back to my oscillator section, you can kind of see how the actual pitch is changing over time. It's basically modulating, let me actually open up an EQ so you can kind of see that. Audio effects, EQ8, right? It's just moving left and right. The pitch is moving left and right over and over again. So an LFO, we've seen an LFO before, right? The issue is you've never seen an LFO on this device before. But what I'm hoping that you'll get out of these lectures over time is you'll kind of understand a framework for navigating any synthesizer. Because truth be told, you just by learning what we learned about the simpler synthesizer, you can almost completely navigate any synthesizer you encounter. It's just learning how to get over the confusion of these confusing interfaces and understanding how the routing works, right? You've seen an LFO before. An LFO is just basically taking something and modulating so that it moves in the pattern of a particular waveform. So for instance, you're actually just basically taking this parameter and you're modulating it using this shape, right? Right? So for the LFO, you can actually change the shape. Instead of modulating it using a sine shape, you can modulate it using a triangle shape. Slightly different sound, or a rectangle shape. And what this is showing, this shape that we're using to modulate, it's like on, off, on, off, on, off, on, off. Right? We're modulating the pitch in this way. It's on and then it's like off. It's just jumping to the other value, right? Whereas if I choose a sine wave, it's continuously changing. But look at this particular, if I go to the rectangle, look at this particular spectrum right here. It's hard to see actually. So the spectrum is not showing necessarily the most useful information in this case, but you can modulate these particular. What happens if I click noise? It's basically changing the pitch randomly. That's what it's doing, right? So if I choose sine, it's basically changing. Remember, what I did was I had to turn on the dry wet control so that the LFO is affecting the pitch, right? So I'm in the oscillator section. The LFO is affecting the pitch, right? Then I have to go to the LFO to actually expose the controls, right? So I'm going to the LFO, and you can see that there are certain parameters that I can mess with. I can change the shape. I could do all kinds of things. I could change the attack, which means that basically the LFO takes a little bit of time to ramp up, right? So if I choose 5 seconds, right? It starts out like not fully engaged. It's like the dry wet control is kind of like off to begin with, and the dry wet control is basically increasing over time, right? So that is the attack of the LFO, right? So let me go back to this particular oscillator section. So what's interesting about this is that you have an oscillator and you have basically a means of modulating some element within this particular oscillator, in this case, the pitch. That's why it's called pitch mod, right? And so this little value right here is the dry wet control for how much modulation occurs for that particular parameter that we're modulating, okay? So let me actually expose another control that's kind of interesting. I'm gonna turn this off. I'm gonna turn off the LFO. And I'm going to go to this square wave. And look at this, a value appears. Notice how if I click any of the other waveforms, these values disappear. Let me go to the square wave, and all of a sudden, this value appears. This is actually a rectangle wave, because this pulse width, let me just play a sound, and you can hear what happens as we change this. This is a perfect square wave. This is more of a rectangle wave, right? Like, because there's two different rectangles here. And when it's a perfect square wave, it's like the left side, the compression of the wave is equal to the rarefaction of the wave, like exactly the same width. So this knob, this pulse width, allows you to change the width of the particular square wave, right? Interesting, right? Now there's an LFO here too. Why would there be an LFO here? What do you think this LFO adjusts? I can't, can you, someone speak it?
The width?
The width. So let's check it out. Now we're gonna go into Dubstep Land right now. I'm gonna click this LFO one. I'm gonna turn up this, I'm gonna turn it up. You see what's going on here? Basically, this width is being modulated. Let me lower the dry wet so it's not doing anything. I'm going to increase the dry wet. You see what's happening? The pulse width is actually moving and changing, right? So I don't know about you, but I'm ready to go to the club now and listen to some dubstep. But basically, this is a very useful parameter to basically be able to put an LFO on. It's pretty rich, right? This might not be your thing. but this might be your thing, right? You see how much motion it gives the sound, right? When you add an LFO, gives it a lot of motion, right? This gives it a lot of commotion, right? So anyway, you have a particular oscillator.
Could you take the pitch glissando off it and compare them?
Oh, sure, yeah. So I'm going to take the pitch glissando off. This is both. So currently the envelope was on. So I'm going to turn the pitch envelope off, right? So let's compare this. Pitch is going up and then down, right? The pitch is going up and down. Now let's look at it when we're changing the pulse width. Right? We're basically changing the width of this particular waveform.
Cool, thanks. It was just hard to tell how much of the pitch mod was the attack and how much was the LFO.
That's a great point. So for instance, when I had this originally on, basically what's happening is the first iteration, it's basically doing this pitch envelope. And then after that, it's continuing on to do, I mean, it's basically doing both of these things at the same time, but the difference between an LFO and an envelope is that an LFO is kind of continuous. It keeps going, right? A pitch envelope finishes, right? It like reaches a sustained value. In this case, the sustained value is right here. So the idea of having both of them on at the same time is this happens, both of them are happening at the same time, but this one finishes first. The envelope finishes before the LFO. So it is indeed hard to tell sometimes what is doing what. So you might have some luck by playing around with both, but a lot of times it just suffices to use one or the other. But there are certain things that you can do creatively, obviously, by exploring both of them. So anyway, there's a lot of interesting stuff that you can do just by modulating certain parameters that are exposed on this layout right here. Now, what's happening next is that this particular oscillator, everything that's being generated here is being sent into this filter. I know that because of this value right here. Basically, I'm saying all this stuff that's here, I want to plug it in over here. And basically the filter F1/F2 is saying, I want to send all of this sound to filter 1, F1, okay? So all of the sound is going to go to filter 1, okay? Now we have this case of subtractive synthesis, right? We were talking about subtractive synthesis a little bit, and that idea is that we're just getting rid of certain sounds, right? Remember how when we actually, can't do it now, but remember how the other day when I was playing let me see. Remember how the other day when I was playing a sine, like a square wave, and then I filtered it and it became a sine wave? Something I forgot to do just now. I can do it really quickly, actually. Let me just show you. Just quick subtractive synthesis, just to show you what's going on. So I'm going to go back here. I'm going to turn off the pulse width, right? I'm going to turn off the pitch modulation. Right? Right now, I have a square wave. What happens if I basically filter out, I change the filter type. What happens if I start filtering out all of the high frequencies? What is this? What is this witchcraft, right? It's actually not that hard to believe, right? We already talked about this, right? A square wave is just a sine wave with a bunch of extra sine waves. So what we're doing is we're filtering out all of the extra sine waves. And what do we get left with? A simple sine wave, right? It's not that surprising now that we've talked about the harmonic series and all of that other stuff, right? But it's cool because subtractive synthesis gives you the capability of doing all kinds of interesting modulations, right? You're basically modulating the amount of the content of the frequencies that are existing in the sound, right? So I'm going to go to filter 1, And basically, what you have to do is you have to set this cutoff frequency. I mean, you'll notice this actually doing something once I actually start affecting the cutoff frequency. So I'm going to play the sound. And actually, it's doing exactly what we just did, right? It starts with a square wave. As I get rid of the higher frequencies, what do we end up with? Our good old friend, the sine wave, right? It's magic. Now, but we have a lot of controls that we can mess with, just like we did before with the simpler device. We spent a good amount of time talking about the filter envelope and what it means for this particular envelope shape, right? Like remember, if you recall, if we go to instruments and we go to simpler, I haven't rewritten all of this for analog. I didn't think it was necessary to include all of this explanation over again, but I do have stuff. But it's basically, remember, what we're talking about when we're looking at this envelope shape for the filter is basically we're moving this cutoff frequency around in time, right? So this frequency, basically when we're adjusting this particular, the envelope right here is pertaining to the value of this frequency knob over time. So right, so what you're seeing is you're basically seeing the frequency knob increase and then decrease. And you can kind of see the waveform stretch out, right? It's starting with a sine wave, it's becoming a square wave. And then after that, it's just going to duck down and become a sine wave again. By the way, the envelope is the dry wet control. This is a really important control. If I turn this to 0, nothing's going to happen. So this value right here, this envelope value, is the dry wet control for this envelope. For this envelope, yes. Right? So essentially, we're just affecting the shape of this particular knob. Which is a form of subtractive synthesis. Now within it, you'll find an array of controls, right? You'll find a bunch of controls that we've seen before, right? Attack, decay, sustain, sustain time, release. Let's just mess around with these. The attack, remember, is how long it takes for the parameter to reach its maximum value. The decay is how long it takes for the parameter to reach its sustained level, right? This is the sustained level. Like you play the sound and it does this shape, and then finally when it's done doing all this stuff, it just literally sits at this value right here. That's the sustained value, right? Sustained time is another parameter here. What it looks like that is doing is it's basically, instead of the sustain staying at a fixed value, it's gradually deteriorating, which is kind of interesting. And the release, remember, the release has to do with how long it takes for the sound to completely dissolve to nothing, for the sound to become completely quiet after you release the key. So for instance, if I have this release really high and I let go, well, this is the filter release, so it's not actually, this is the filter release. So the amplitude, if I go to the amplitude envelope and I make the release really high, it's still sustained, right? No hands, right? If I make the release shorter and I let go of the note, it immediately dissolves. So remember, just like with simpler, you have an envelope for the filter and you have an envelope for the actual amplitude, for the volume of the sound. So you might choose to have a different envelope for your filter than you do for your amplitude, right? So let's take a look at this. There's a lot of parameters here, but ultimately you don't have to learn what all of these parameters do. this graph itself will suffice for most of your needs. This value right here is very important. This knob right here is very important. I should make a big 3 about this particular device. But in short, if you don't set this envelope, this is the dry wet knob. So if you set this value to 0, it's not, this knob won't ever change over time. The value of this cutoff won't change over time as described by this graph. Whereas if you set this knob to be really high, this particular shape will influence the parameter change of this knob, right? So you need to set this value higher. I remember in previous iterations, I'd forgotten to set this knob and people were like, why doesn't the sound any different? Well, this is a highly important value, a highly important parameter on most synthesizers. When you look for this envelope value, it's basically telling you how much the envelope is affecting the parameter. So make sure you set it to be something. Okay. Great. Let's take a look at, and again, you have this LFO, so you can actually, you can change let me turn down the envelope, and let me just let's listen to the LFO. So in this particular case, it's not even looking at this anymore. It's just basically using the LFO to change the value of this. Wow, 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 right? So this is the dry wet knob for the LFO. I want to have the envelope on. This is the dry wet knob for the envelope, right? Great. Now, if I go on to the amplitude section, same kind of parameters, right? You'll see an envelope for the amplitude, meaning if I change this value, if I change the attack to be really slow, it'll take a second for the sound to actually reach its maximum amplitude. Or in this case, 15 seconds, I should say. Ah, look at that. Look at that value, just increasing. Right, isn't that cool? It's actually, you might not hear it increasing, but it's actually increasing over the course of 15 seconds. I'm not going to subject you to hearing that for 15 seconds, but let's just do a shorter example. Let's do 3 seconds. 1 Mississippi, 2 Mississippi, 3 Mississippi. It stopped, right? After 3 Mississippis, it stopped, and then it actually ducked down, right? So let's do that again. 1 Mississippi, 2 Mississippi, 3 Mississippi, and then it sustains at this value. You understand what's going on there? Let's do 5 Mississippi. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, right? It's going to take 5 seconds for it to reach its maximum value, and then it's going to duck down to its sustained level, right? Not its time. This is a level. So it's going to take 5 seconds, and then it's going to jump down to the sustained level. And how long it's going to take to get to that sustained level is this decay time. Okay, so you're seeing a whole swath of controls, right, for the filter, and you're seeing a whole swath of controls for the amplitude. But more or less, all of this stuff is stuff that you've seen before, right? It's just presented in a different way. But if you were agonizing, like if you were left on a desert island with this synthesizer, and you were just equipped with the knowledge you had to operate the simpler synthesizer, you would be able to figure this out because the principles are the same. It's just knowing what is where. And what's really helpful in that scenario is just hovering over any parameter and looking at the bottom left-hand side of your screen and looking at what the help info view tells you, right? So on the bottom left-hand side of the screen, it's telling you its cutoff envelope. The slider sets how much this filter's cutoff frequency will be modulated by the filter's envelope. Great, right? It's just telling you how much this is relating to this, right? I don't think I need to tell you what key is, but I'm sure someone is curious. So if I set this value up, you're going to see this in all kinds of synths, so I might as well tell you. If I set this value to be higher, basically depending on which key I'm playing, you'll have a different value of modulation. So if I play low notes, the frequency modulation will be less intense, than if I play higher notes. Let me lower the attack so it's quicker. Let me change the attack. Let me actually turn that off now, and let's see if we can hear a difference. Basically, it just changes. The idea is you might not want to apply the same cutoff to a lower frequency that you want to apply to a higher frequency. So this sort of tracks that motion so that you apply a different cutoff frequency. You apply a different cutoff amount to higher frequencies than you apply to lower frequencies. So you can experiment with this and listen for the differences that this modulation affects in your sound. But, and you'll see this all over the place. So just be aware of that it exists and that you can mess with this. Resonance mod. Well, it sets how much the filter's Q will be modulated by note pitch. So the sharpness of the filter. Let's turn this up all the way. Let's actually turn on the LFO. Interesting. Interesting. So the filter itself, remember, has a certain sharpness to it, right? So if I turn on a specific filter node, right? This is a particular filter band that I'm messing with. And if I adjust the Q, it actually makes it narrower, or steeper, or narrower, right? So what this allows you to do, you can actually modulate this by how steep or shallow this particular shape is, right? So what this particular parameter is modulating is the steepness or shallowness of the particular frequency, of the particular filter band. So if I set this to be really high, what you're seeing is the filter become really resonant. It becomes really resonant at really high values, at really steep values, and it becomes less resonant at shallower values. You start hearing at really steep values, you start hearing a particular pitch very, very clearly. And you can see that in the graph, right? You see that certain frequencies become really, really punctuated when the resonance increases, whereas other frequencies, when it's not, the frequencies aren't as punctuated. So that's something you can play around with. So what is the kind of signal flow going on here? You have an oscillator, right? You have to choose a particular shape of waveform. Then you have a filter. You filter the sound using subtractive synthesis. And then you basically adjust the volume of the sound, right? You can put an LFO on the volume, right? For the level modulation, right? So for instance, I could do something like this. Let me turn off that filter resonance modulation. And basically you're seeing the sound disappear and reappear, right? Which is very similar conceptually to filtering, because when you're filtering, you're basically causing certain amounts of the sound to appear and disappear. Whereas here, you're causing all elements of the sound to appear and disappear indiscriminately, not caring about frequency, just caring about the entire sound, the volume of the sound, right? Yeah.
A question about the LFO. So my understanding is that there are 3 parameters. One would be the rate of the LFO. Second would be where the cutoff frequency starts, like at what cutoff frequency it's oscillating around. And then third would be the amplitude of the LFO, like how deep it goes. Could you show us those parameters?
Sure, absolutely, yeah. So I'm gonna use the current so currently I'm gonna modulate the volume of the particular sound. And I'm gonna show you the LFO section now. So the LFO section, if I change the rate, basically you're gonna see this. You're gonna see basically the number of repetitions per window of time increase, I should say. So you're basically having faster repetitions. You're basically modulating the parameter more quickly. If I lower this rate, it's actually decreasing how fast this kind of periodically modulates, right? But, and so this control is exposed right here. So you don't actually have to go inside menus to find this control. It's just exposed right here, right? You could also adjust the rate of the modulation in terms of beats, right? So quarter notes, half note tuplets, half notes, 16th notes, right? So if I turn on my metronome, right? So it can sync up, it can synchronize with your metronome, right? So that is the rate. That's one of the three components of an LFO, right? The other thing that we've talked about is the shape of the waveform. So you can have, right? You can have, if I have a sine wave, it's continuous, right? You hear it continuously changing. If I have a rectangle wave, it's basically going to be jumping. Right? So there's basically the rate of, there's basically the wave you choose to modulate, right? This is the wave that you're using to modulate the other sound. That's the waveform. That's one of the controls you have. The other control you have is the rate at which you basically change another parameter, right? The rate of modulation. And the third parameter is basically the amount of modulation. So on this control, in this layout for analog, you access the amount of modulation on the particular parameter side of things. Like you don't access it on the LFO side of things. In other words, like you adjust the depth of the modulation on the parameter, like you find it on the relevant parameter window. So for instance, if I want to adjust the depth of the LFO, like how much the LFO is modulating the amplitude, I would go to the actual amplitude section, and this is like the dry wet knob. This is the depth of modulation. So if I have it set to 0, it's not, let me turn off the envelope. Well, actually, it's fine. There's a frequency envelope. Give me 1 second. 1 second. Okay. Okay, great. So I've got this nice bright sound. Great. So if I want to affect the LFO on top of this particular parameter, like if I want the LFO to affect the amplitude level, I would go to this parameter right here, the level mod, and this controls the depth of this modulation. Right? I access it here and not here for this particular synthesizer, right? So I can, not all synthesizers work the same way, but on this particular synthesizer, so those are the three parameters, right? Like the waveform you use to modulate a particular parameter, the speed at which this modulation occurs, and the amount of modulation. So those are like the big three that I would pay attention to.
Cool.
Yeah.
Would there not be one more parameter, i.e. the cutoff frequency, like where you're oscillating around? And it looks like Sean says that might be specific to the envelope you're using. Like would the envelope define where that cutoff frequency is?
I think what I was saying is if you're modulating the filter, then you modulate around a frequency, but if you're modulating amplitude, then you modulate around a certain level. So
right. Okay, that is another important parameter actually. Yeah. So like the base value at which you're modulating, let me write this down. Oh, my snip notes. I just restarted my computer. This is an app I love, use it all the time. Just to type in quick notes. 4 parameters, LFO. Okay, so the idea, yeah, so precisely. So the other parameter that you have to pay attention to is, where did my synthesizer go? The other parameter that you have to pay attention to is basically what value you're oscillating around. So for instance, like Sean said, for a filter, basically the LFO is kind of centered around this frequency. For if you're modulating, if you're using the LFO to modulate the filter cutoff, it has to modulate around a certain value. So it's modulating around this value right here. So I'm going to play the sound. I'm going to go to a sine wave actually. Right? I'm going to change the frequency value. And you can see how that has an impact on the sound, right? Because it's basically modulating, it's applying that shape around a lower frequency, but now it's applying the shape around a higher frequency. So one problem that people have actually when they're working with envelopes and LFOs is that they set their initial value to be too high or too low. And that's not giving the LFO or the envelope any room to work with. Because it's basically, if it's trying to move this dot to the right, well, it's got nowhere to move it to, right? It's already set to the rightmost spot, right? So similarly, if you're using an LFO, if you're like, notice how it's doing less stuff at when the frequency is set really high than when it's set really low, right? It's just different. So that's absolutely that's absolutely true. So you have to recap, you can choose the shape that basically what shape the parameter is being modulated around. Like is it being modulated by a sine wave shape or is it being modulated by a square wave shape? What rate is the modulation occurring? Basically what depth of modulation is occurring. So like basically if you go here, you can set the depth of the modulation, or you can have it and that on the analog synth that occurs on the parameter side. So like on the parameter you're trying to modulate, you find the control there. And then you can control that basically at what value you're basically modulating around. So like if you set the value really high, you're modulating around this value. If you set the value really low, you're modulating around this value. So again, I want you to not feel intimidated by all of this, because I'm not exaggerating when I'm telling you, like, as we keep going over this, like you will, to a huge extent, know 90% of what you need to know about synthesis just by exploring these simpler controls, literally these simpler controls, but on the analog device. But these particular parameters appear all over the place. Like when we look at the wavetable device eventually, when we look at the operator device eventually, as we've seen in the simpler device, you're going to see these parameters. You're going to see an oscillator section. You're going to see some sort of pitch envelope where you can adjust the pitch. You can adjust it by an LFO. You're going to see some filter section where you can adjust the cutoff frequency by some envelope or by some LFO, right? If you're just basically adjusting this value, right? You're going to see some amplitude envelope where you're basically adjusting the level, right? You're basically adjusting this knob, like in some shape, right? Or some pattern, like it could be an envelope where it just kind of settles into some value, or it can be an LFO where it kind of just bounces and wiggles until you let go of the note, right? These are amazingly robust things that people discovered 60 years ago or more, even more. So, I mean, these particular fundamentals of synthesis will take you a long way in doing a lot of great things. And of course, you can adjust the LFO parameters in the way that we've just described. But in other words, like when you're trying to construct a sound and you're trying to use a new synthesizer, try to figure out where these parameters exist. Like instead of trying to like rack your brain around every single side thing that it exposes, just be like, where do I choose the basic wave shape of my sound? Just search for it and be like, oh, here it is, oscillator 1. I can choose the shape. Where can I filter the sound? There's a filter section. Where can I adjust the amplitude envelope? Here's an amplitude envelope section, right? Granted, this is a more complicated synth. In reality, a lot of the synths that you download won't be as complicated as this. Some will be. A lot of the analog synthesizers that you encounter won't be this complicated. So if you can wrap your head around this and different flavors of this, you're really well equipped to kind of being able to handle a lot of things. So that's why these concepts are being tested on your homework and will continue to be tested, I think, for the final homework as well. So don't feel discouraged, just feel empowered by all the capabilities that are afforded to you. So anyway, I know that was a lot of information. Harmonic series, that whole conversation about the math may have just gone in one ear and come out of the other. But I hope it kind of made some sense, and it will, you know, these concepts will kind of rear their heads in various shapes and forms. Like we've kind of talked about how when we were looking at a spectrogram, we're kind of inadvertently kind of viewing, it's kind of related to additive synthesis in a lot of ways, right? So anyway, eventually we'll talk about vocoders, and this idea will come back into place again. So anyway, with that being said, I will pause recording and just let people